All right, welcome to this explainer. We are about to uncover the genuinely awe-inspiring reality of gravitational time dilation. You know, if you've ever found yourself wondering why gravity isn't just this invisible force pulling your coffee cup to the floor, but is actually something that physically warps the clock ticking on your wall right now, well, you are in the exact right place. Okay, let's dive right in with a massive question, something straight out of science fiction, just to see what extreme gravity actually does to time. Picture this. You take a quick trip down to a planet, you hang out for just one single hour, and when you get back, you discover that 7 entire years have passed for all your friends back on Earth. Now, how is that physically possible? Spoiler alert here. It is absolutely not movie magic. It's the actual literal physics of our universe.
Section 1. The Cosmic Speed Limit. To solve this mystery, we first need to establish the unbreakable rules of our universe.
So first things first, space and time are not independent. They are interlinked into one geometric fabric. Now, for centuries, humanity basically thought space was just an empty, rigid box, right? And time was just a clock ticking away at the exact same rate for everyone, everywhere. But actually, scratch that. They are woven together into this stretchy, changeable grid called space-time. You literally cannot mess with one without messing with the other. And that brings us to a really foundational rule. Whether you are just sitting stationary on a park bench or you're flying on a rocket at 99% the speed of light, light always travels at the exact same speed. Represented by the letter C, the speed of light is the ultimate, absolute constant. It never speeds up, it never slows down. No exceptions. Section 2, the warped rubber sheet. Let's visualize exactly how gravity fits into all this by telling a little story about light. Imagine a completely flat rubber sheet, or let's say a flat mattress. This represents our empty space-time. If you roll a marble straight across it, it travels in a perfectly straight, short line. Simple enough, right? But what happens when you drop a heavy bowling ball onto it? That bowling ball represents a massive object, like a star or a planet, and it pulls the fabric down, creating this deep dip. Now our marble, which represents a photon of light, is forced to travel a much longer, curved path down into that crater and back out again. The space itself has literally stretched. Section 3. The math of slow time. So how exactly does a curved path on a mattress equal slower time? This is where it gets really mind-bending. Think back to middle school math for a second. Time equals distance divided by speed. Now, if our speed of light is completely unbreakable, but the distance it travels is stretched out by gravity, basic physics dictates that time itself must slow down to balance the equation. Think about it. If the distance gets longer because it's dipping into that bowling ball's crater, but the speed of our marble absolutely cannot change, then the only variable left in the universe to alter is time. The universe essentially hits the brakes on the ticking of the clock to allow the light to cover that longer distance at the exact same speed. So more gravity equals a longer path, which guarantees slower time. Section 4. Proving it with airplanes. And you know, this isn't just abstract theory on a chalkboard. Scientists actually proved this right here on Earth. Back in 1971, there was this incredible test called the Hayfel-Keating experiment. They took super precise atomic clocks and literally flew them around the world on commercial airliners. And guess what? They actually gained or lost nanoseconds compared to clocks left on the ground, exactly as relativity predicted. Why? Because the airplanes were flying high up in the atmosphere, meaning they were further away from Earth's center of mass. Going back to our analogy, they were slightly further out of the bowling ball's dip. Because the space-time up there is slightly less warped, the distance light travels is slightly shorter, meaning those atomic clocks literally ticked faster up in the sky than the ones down on the ground. Section 5, Extreme Gravity. Now, let's take those tiny little nanoseconds and scale them all the way up to the mind-boggling extremes we teased at the very beginning. Think about Miller's planet from the movie Interstellar. The immense gravitational warp of that supermassive black hole, Gargantua, meant that spending just 1 hour there equaled 61,320 hours passing on Earth. That is 7 full years. If Earth is just a bowling ball on a mattress, a supermassive black hole is like a mountain, crushing the fabric of space-time into a near bottomless pit. The distance light has to travel through that warped space is so incredibly vast that time practically crawls compared to the relatively flat, safe space back on Earth. Section 6, falling into the dark. But what happens to time, and more importantly, what happens to you if you don't just orbit a black hole, but actually cross the absolute point of no return? Surprisingly, as you fall past the event horizon, you wouldn't just plunge into total pitch blackness. Because light is still falling in right alongside you, you'd actually be able to look back out. And because of the severe time dilation we just talked about, you'd watch eons of the universe's evolution flash by in an instant. It sounds beautiful, right? But physically, it is an absolute nightmare. Before you get very far, gravity accelerates your feet incredibly faster than your head, shredding you in a brutal process that scientists actually literally call spaghettification. In less than a microsecond, your matter is stretched and crushed into fundamental particles. From there, your crushed remains would plummet directly into the singularity. This is a point where the mathematics of relativity break down entirely and all paths literally terminate. As astrophysicist Jan Levin bluntly notes, it is an end to existence. It's essentially a puncture right through our rubber sheet. The matter that fell in is effectively permanently removed from reality.
So, as we wrap up this explainer, I want to leave you with a pretty provocative thought. Does falling into the dark mean the ultimate end? Or could your crushed remnants actually become the building blocks of an entirely new universe? Because our equations completely break down at the singularity, some physicists speculate that instead of absolute non-existence, all that highly compressed matter might rupture out the other side as a white hole, sparking a brand new Big Bang. It's definitely something wild to think about the next time you try to wrap your head around just how weird and wonderful our universe really is.